All right,
Are you recording?
action.
Hi guys, this is Mr. Manis's AP Physics class.
It is.
Grade
I'm gonna
5.
put this so I can see myself. And
So very fluffy.
okay, I wanted to start out with something that if you have an angle here, that angle times the radius equals this distance here, this arc that this angle subtends. By subtends means underneath this arc. Do you guys know that?
Now we do.
Everybody know that? Everybody on board with that?
Yeah.
You should
Okay.
come out.
It's D, when the angle is small, D approximates S. Do you see that as the angle is smaller?
Yeah.
So, for both of these, you can kind of figure that out. I wonder if I'm focused here. I'm kind of zoomed in. That's why I need to see who there am.
Oh wait, but it's stop.
Oh.
The focus is wandering. There goes. Is it gonna stop? Okay. So sorry about that, YouTube people. It's all messed up. I need a haircut really bad too.
I can see your bald spot.
You can see it. Okay.
Oh my gosh,
If now if you understand this, at the same radius, if you have a change in the angle, you guys see that this is going to be true?
what?
Do you guys understand this? If I change the angle, if I make some small change in the angle, so if that's this little change in angle will be delta theta, that this is going to equal delta S up here. You guys see that?
Yeah.
Okay. So if I divide both sides by delta t,
Why are you divided by delta t?
you'll see in a second.
Okay.
What does delta S delta t equal?
Velocity?
Velocity. And then I'm going to define delta theta over delta t as omega. And I'm going to call that angular velocity.
Is that a W?
It's an omega. That's a lowercase omega. This is an uppercase omega in the Greek alphabet,
Oh, okay.
and this is a lowercase. It doesn't really look like a W. It looks like kind of
What does it mean?
like a
But.
butt.
What does that mean?
Yes, so.
I didn't want to, I gotta keep it clean because we're on
Right, I don't
YouTube.
feel it.
They say bad things on YouTube.
Oh.
No, I know, but I mean, I don't
He's
I
a
don't want
teacher.
actual evidence
Oh.
of bad jokes or whatever.
Getting
Okay,
it.
so you can plug this in. You can substitute if this is 1, 2, and 3. You can substitute 3 into 2 and get this guy right here. Get R omega equals the velocity. So if I have a wheel spinning around, so let's draw a little wheel. Wheel spinning around like this. I have the angular speed, which will be in radians per second. That's what the units here, radians per second. If I multiply by the radius, r, I get the velocity, but the velocity is changing direction all the time. But the omega is not. And omega could be a vector too.
Is the
And I'll explain.
velocity like a tangent one?
Exactly. The velocity is a tangent of the circle, wherever it is at any given time. So if this is a little car, like our little car going around the racetrack, that velocity is a tangent. And if omega could be a vector or a scalar. If omega is a vector, it's the right-hand rule. It's what, use your hand, your right hand, in whatever direction your fingers are going, and the vector would actually be pointing out of the board. So for all these angular components, like angular acceleration or angular velocity, you use the right-hand rule for all of them. So if it's going counterclockwise, the vector is pointing out of the board. Use your right hand. The thumb would be the vector. Okay? Is there any questions at this point? I'm not, I didn't follow your question.
Like, you know how you said the vector's going out of the board, or when would it not be?
If it's going clockwise, it'd be pointing into the board. But it's always like, it's like perpendicular to the plane of rotation.
Okay.
That's how these are, because you can't have it here, because this is always changing, you know, so that would make sense to put it there. So what they do is define it as point, going out or in, along, perpendicular to the plane of travel.
On equation 2, why are the two things equal? I don't understand that.
From equation 1, from this, I understand that if I make a small change in the angle theta, I'm gonna make a small change in the distance that's subtended by the angle.
Oh, that's an R?
Yes, that's the radius.
Oh, let's say when I thought it was a V.
No, this is R, I'm sorry.
Okay. That's just confusing me.
Yeah, those italic V's tend to look like R's. I'll try to make them look more like this guy right here. Any other questions? Okay, so, then it follows, that if you have, you can write this as well, R times delta omega equals delta V, and I can also divide that by delta T. And I wind up with a new term I have to define as delta omega, that's change in angular velocity over, change in time, is angular acceleration, which I'll call alpha. So that's an analog, or an analogy to linear acceleration. And omega is an analog to linear velocity, yes.
You're only dividing the change of the W thingy by T, not the R, and the fifth one?
And the fifth one?
Yeah.
Yeah, I'm dividing this because I'm gonna take, this equation, number 6, and substitute it back into 5. So that, I should probably put these definitions, right, like definitions. Just to show that they're definition. I'm gonna flip this around. And I'm gonna use the 3 equal sign. You guys seen that?
No.
That means I'm defining it. I didn't derive it, I'm defining it this way. Delta omega over delta t. No, delta theta over delta t. And this one's gonna be alpha equals delta omega over delta t. Questions? Let's let somebody's hand go over. No? Okay, so,
Is R always constant? Yes.
yeah, R is constant in this case. R can change, but yeah, that's beyond this class. Yeah, go ahead.
So what is W? Like, what's the term for it?
It's not a
Or
W,
alpha, omega? No.
Omega.
Yeah.
omega.
Yeah, what is that? What does that represent?
The amount of radians per second that the object is covering. Like so, angle is in radians, not in degrees.
So, how it changes per radians per second?
Like that the velocity's covering?
Yeah, so 1 revolution per second would be 2 pi radians per second.
Okay.
Does that make sense? Because in 1 revolution, there's 2 pi radians. And radians don't really have a dimension. They're just a kind of a fill-in unit, but they don't have a dimension like meters do.
And then what is angular acceleration?
Angular acceleration is when this omega, this value omega is changing.
Oh, okay.
So that's,
This could be a derivative too. So for your calculus people, this could be delta theta over delta t.
yeah.
I mean, sorry, d theta dt. And this could be
That's
d theta dt over ds dt.
Wait, so
So if you want to write it that way, that's fine with me. I just don't want to
Can you
make
find the answer
the,
to
I don't want
it?
to make the non-calculus people mad at me.
Can you find the answer to it using the derivative?
Yeah, if there was some more math other than just dividing these, making these differentials by dividing, yes, you can take a derivative. You would be taking the time derivative, and that's what you're doing. But you don't know what theta, if there's a function in theta, if theta is defined by a function of time, then it would be the first derivative of that theta.
That's fishy. What's
And this fishy is also coming out of the board too. Its vector would be popping out of the board.
Do you have
at
to
you.
know like your radians to do this?
What do you mean by know
Like
the
your
radians?
Like
radian measurements and
Just
stuff?
know where they're at.
Like is it?
Just remember that, one turn, one complete rotation is 2 pi. That's all you need to know. Yeah.
I don't have to use the unit circle to look at the radians.
No, I don't think so. No, because it's going around and around and around. It's not like going so far and parking, not usually.
Okay.
You might, you might run into that on one of these equations, one of the problems. I haven't looked real carefully at the problem set. I'm gonna do that after you guys leave today and pick one and send you a problem set. That's basically how you get these equations. These are analogous to velocity, acceleration, and distance by time, because you can multiply this by time and get how many degrees or how many radians the object has moved around the circle. You guys get that?
Say that again.
If you take omega, if you had an angular momentum omega and you multiply by t, you're gonna get theta back. Right? Does it die? Oh, no. You guys see that? So t times omega is theta. So if you know, at a given time, you can find out how many radians has elapsed. How many radians is this covered, has the car
Using the
covered?
ankle,
Yes.
but wouldn't it give you, delta? Like, would you multiply by delta?
You could put delta, but t works too. I mean, yeah, you can do that as well. Delta t, delta. It's just this equation, just rearranging the definition of omega. Okay, so everybody's got these down? I'm gonna erase this. Okay.
Fishy.
Now, I want you guys to do a thought experiment with me.
I hate thinking.
I know, well, you came to the wrong class if you're thinking. If this is 1/2 m, and this is a little wheel, and you have another 1/2 m over here. Oh, that's 1 over m, that's bad. 1/2 m.
Bad.
This is a point mass. So in other words, it's a lot of mass in a very small area. Now, if I try to rotate, would there be some inertia when I went to rotate this? Do you guys know what inertia is? Inertia means resistance to change.
Yes, that one.
If I try to spin this, if this is on an axle and I try to spin it,
What depends which way? Like,
either way, if I try to spin it up or spin it down, would there be resistance to that change?
No.
Is
Wait,
there friction
what is the other
on
one?
what it's been?
There's no friction. There's an axis going into the board.
well, I think so.
No. There's an, would there be?
There's an issue though.
Well, let's get a consensus.
Because it's
For what?
gravity.
If it's rotating?
They're gonna fight against gravity when they go in one direction, right?
Well, they balance each other out, so gravity is not really in play. It would behave the same as it would in space. Like with the balance, it would behave exactly the same in space. Because you got a force, the force of gravity pulling down, and that makes this go up, and the force of gravity is pulling down here, which makes this one go up, and they both balance each other out.
That makes sense.
But if it's rotated up like this, then there's no force of gravity on either one of them as far as the pivot point.
Unless you push it, right?
You tip it.
Yeah, if you tip, what I'm saying is it would be the same, as easy to push here as it is up here. There would be no difference because the forces are canceling each other out. Now, would there be resistance to speeding it up? If I spun it, if I just tapped it, would it spin infinitely fast?
No.
No.
Maybe if you're in space.
Nope.
No.
Nope. What do you guys think? What's your gut intuition tell you? Is this resisting change and speeding up angularly?
Angularly? No.
Yes.
Yes,
Yeah. Because if I double the mass, wouldn't this thing be harder to turn?
Yeah.
Yeah, that's, so
Doubling
it's,
on both sides?
yeah, if you double it, if you made this 10 kilograms and 10 kilograms instead of a half a kilogram, it's gonna be a lot harder to turn.
Why is it M?
Yes.
In, just mass. I'm just using a generic, like, mass.
Okay.
Okay? So, now what if here's another thought experiment. What if I double the length of the arms and put the mass out further?
Same thing.
Would it be harder or easier to rotate or the same?
Easier.
Be harder, much harder.
Why?
Because as you put them out, remember that the resistance of changing in velocity is would be increased out here because the change in velocity would be increased out here. So if you change the velocity enclosed, you're not changing the velocity as much as when it's out here. Like if you thought about the linear momentum here and the linear momentum here, the linear momentum here would be greater, it'd be twice as great. Right? Yes.
But can we ever stay into like the farther it is away from the axis or the spinning axis?
Axis point, yeah.
The axis point, then the easier it is to move.
No, you're thinking of a
Turk.
yeah, you're thinking of a torque and maybe a lever. So if I have a fulcrum here and I have a mass here, the longer the fulcrum, the easier it is to turn.
Why?
Well, that's because you're increasing the place that you're pushing on. So you're making this go way out of here. You're putting a force here. That makes this easier to move. It's lever action. You're getting mechanical gain is what it's called.
Okay.
But that's not what I'm doing here. I'm actually making this part further out. I'm putting the mass further out, not where you're pushing from. I'm pushing from the same spot. If this is where I'm pushing, I'm hitting this with my finger. If it's further out, is it going to be easier or more difficult to accelerate?
More difficult.
More difficult. You guys are falling asleep on me. I still got
I still
five.
don't understand why it would be more difficult.
Do you understand that if, say I hit this with my finger going 2 meters per second, and this was at 1 meter. If this is at 2 meters, what's the velocity gonna be right here? 2 meters per second. Oh, no, you're right, it was 4. Yeah, because I was thinking of 1 meters per second. Do you see that?
Yeah.
Yes.
Now, if that arm is extended out here, then this is gonna be 8 meters per second. Right? So that is a bigger change in momentum. That means, and remember that force, Newton defined force as change over momentum over change of time. And this would be a vector and this would be a vector. You guys remember that?
Yeah.
So if you have a bigger change in momentum, it's gonna require a bigger what?
Force.
Bigger force.
No.
Okay, now it makes sense to you. Okay, so we're gonna define I as the resistance of change in angular acceleration.
What?
I.
I didn't understand what your question was.
No, I'm making a statement. I is the change, I'm gonna define I is the resistance of change of angular momentum. You guys might wanna write that down. Will, get up. Stay with me, dude. Because you're not gonna get this from hippocampus.
I is changing momentum.
I is not change in momentum.
Angular.
It's change, it's the resistance to change in angular momentum. So it's like mass in linear terms. And it's defined as mass times this radius squared.
Is this supposed to change in what?
Change in angular momentum.
Okay.
Okay?
I'm so hungry.
So if this is the inertia, if this is the like kind of the angular inertia is kind of the way that you can think about it. There's also an analogy of force, but we're going to use a Greek letter tau is I times alpha.
What's tau? So for-
Tau is torque.
I thought we were gonna talk about torque.
Did I spell that right?
I don't know, you're the physician.
Torque.
I spelled terrible.
Get it right.
Did I have it right?
No, QUE.
Yeah, spelled it right. Okay. So this is angular acceleration, this is the angular inertia, and that's the angular force. So this is just like F equals ma, right?
Wait, what is alpha mean again?
Alpha is the angular acceleration.
And
So the analog in the linear world would be F equals mass times acceleration. In the rotational world, it's torque equals the moments of inertia times the angular acceleration. And guess what? All the canonical equations apply. Yeah.
can
So delta theta equals, let's see, omega times time plus 1/2 alpha t squared. So it's the same thing.
So they're just different like variables kind of?
Yeah. But you can figure out what the change of an omega is, or a change of theta is, by knowing what the omega times time.
How?
Just plug it in. If there's no angular acceleration, then it's just time times omega gives you the change in theta.
Okay.
Got it? And all the other ones apply too, so, let's see. The other one was, let me write down the linear ones. V squared equals V sub 0 squared plus 2a x2 minus x1, or y2 minus y1. What, just depends on what. That's so then this will be true too. Omega squared equals omega 0 sub 0 squared plus 2 alpha times theta 2 minus theta 1.
Are there different ones for like X and Y?
There is no x and y in circular.
So it's just the same?
Yeah. There's no x and y in rotational motion. It's like using polar coordinates. You've got r
Oh, yes.
and theta are your two coordinates. Let's see. And then there's the last one. Which are the canonical equations? Oh, it's omega equals alpha times time. So these are your canonical equations in circular rotational form.
Can you, give me the definition of the torque?
The torque, this is the definition of the torque.
No, like in words.
Oh, torque is equal to you could call this angular inertia or the moment of inertia times the angular acceleration. Moment of inertia times angular acceleration.
So like torque is angular force?
Torque is, yeah, it's like angular force, yeah. It's like force in a circular system. So how fast this starts rotating is proportional to the torque that you put on the system. Okay? So if you double the torque, what do you do to the angular acceleration?
You would increase.
You double it. It's linear. It's a linear relationship. You sleepyheads are gonna be struggling when it comes time to do some problems here. Okay.
I'm not struggling anyway.
No. Will's drooling.
It's super early.
You're gonna need this, dude, to do problems.
Oh, well.
Can you, I wrote all this down while you were going to give me.
I want some grilled cheese.
And shouldn't be changing, for the first one, shouldn't be changing data, not data change.
Which one?
The first one.
Yeah.
This one?
Turn off.
Yeah, all these Greek
Yes, sir.
letters,
Oh, yeah.
Delta theta.
Dude, I heard they're making RV storage across the street instead of fast food.
I don't know that. I don't know what it is.
Okay,
Wait, hold on. I just-
now we gotta talk about different shapes.
Like oval.
Have different, not ovals, but like, if you have a stick, I'm gonna erase this, just copy it off somebody else. If I have a rod,
You mean like shapes moving and rotating?
yeah, shapes moving in rotation, if I have a rod with an axis through it and it's rotating around this angle, the I is equal to its length. And this is uniform mass. Do you guys know what I mean by uniform mass?
You can't change.
Yeah, this is uniform mass across here. That means it's not heavier here than it is in the middle. It's not, the density is constant through the whole rod. Okay, the I equals L squared. Here, I need room. It's 1/12 L squared,
And 12.
times the mass.
That's
Here,
just
let me
the
put the
formula.
mass here.
Is there a random?
L squared, there we go.
So I also equals MR squared.
Yeah, there's your R, right? To get this, you would need to actually do calculus. You need to do an integral to like, figure out what the angular momentum is. You basically make a little, did you do three-dimensional, triple integrals?
No.
You didn't? Well, you basically find the volume of this and the density, and you'd integrate it across the whole rod. And that would give you the moment of inertia. You would, I could show you, but no, you guys will kill me by the end. But you can show that if you have a rod of equal density, its length squared times its mass equals 1/12 times its mass times its length equals its moment of inertia. This would be its mass in kilograms if this is in SI units.
Why did 112? Where did 112 come from?
From the integral.
Oh, okay.
Okay, and then if you were to extend this rod, if the rod is like swinging off one side of the axis, then the moment of inertia equals 1/3 M over L squared.
Why?
You've translated it
Oh,
out
instead
here.
of in the middle, you put
Yeah,
it to the
yeah,
side.
you just, this is still length L, and you can imagine it would be a little harder to turn if it's out further, because more of the mass is out further from the radius on average.
I still don't understand the coefficient.
I don't understand.
Which coefficient?
Both of them. Like, why is there fractions?
You don't understand what,
The 1/12 is just part of the definition, right?
no, 1/12 is what you get when you actually do the interval. You'd have to do some math that none of you have had yet, so for me to be able to show you where it comes from.
But it's just part of the definition.
No.
So. if
Yes, you can use this definition and you put it in an integral form and you would get 1/12 out of it.
So we don't use that one or something?
You could if it was just a single point mass.
No, but when we're trying
What
to
is it,
find.
what is it?
If this is, check this out, you can use the definition when you have this situation. If you have a mass M at radius R and you're swinging about this axis, you could find its I, you could find its moment of inertia,
Oh.
What?
okay?
No.
I understand.
That's how you would use the definition. You have a fixed mass that's swinging around, like say you had like, some rock on the end of a string and you're swinging around. If you wanted to find the moment of inertia of the system, it's the distance of the swing times the mass of the rock. That's how much it resists the change in speeding up. Did I answer, you comfortable with that? Yeah? Anybody else?
Define inertia.
Inertia is the resistance of change. So Will and I have more inertia than Sweden. Because if we were in a rolling chair, you would have to put more force to get us moving than we would in Sweden, right?
I didn't know.
Probably like 3 times the force to get the same acceleration.
Will's about like,
He weighs almost as much as I do.
Will is broad.
I
Well,
can't
there's a lot.
imagine moving it.
Cause you said you weighed how many stones?
About lost so much weight now.
It was 20 stones, I think you said, so that'd be 280 pounds.
Yeah, no, I'm not very anymore. I'm like 260.
Football.
Yeah.
So yes, you can use the definition of moment of inertia.
I'm 660.
Okay, well, my question is.
You can use the definition, but only in this situation where you have a point mass at a fixed radius. So it's a very special situation, but what if you're rotating something like a disc?
Then it wouldn't be a point mass.
Then it's no longer point mass. And I believe the disc is I equals 1/2 ml squared.
So where do you like? where do you-
Coefficient changes with the object, right?
Yes.
Oh,
You use the
okay.
integral to find it.
Yeah, you would need to do calculus stuff.
So would they give you the? So
Yes, there's a table in here. I'll tell you what page it's on. And let me double check the disc. See, this wasn't in hippocampus. You guys would be like definitely coming to me like, you didn't tell us this stuff. Yeah, I was correct. It's on page 208. So I'm not gonna bother writing them all down, because you could just look in your book. But the disc, when we say, this is a radius, you could say this is big R. That'd be the same thing though. And then they have a washer, and you have to know the inside radius of the washer and the outside radius. You guys know what a washer is? It's like a donut shaped piece of metal.
Yeah.
I think we used, right?
Yeah. And a thin hoop, like if it's just a thin mass, or a thin hoop like a hula hoop filled with lead,
That really doesn't.
it's just I equals m r squared.
Wait, why?
Because it's the same as just putting a mass out at the end of the end of the, you're just distributing that mass over the whole circle. But it resists the change in the rotational motion just the same. Alright?
What page was it on?
So the rest of, all this stuff you treat, just the same as, the linear momentum problems, because you use the same, analog equations, the same,
What the heck?
they're just different variables.
Sorry.
But there's no projectile motion. You don't have to do projectile motion because it's rotating, I know.
Oh, we should record the.
Okay, so you would be able to look them
On the
Okay, so, any questions?
These are all of the equations we need to do the problem sets.
I think so.
and so
I
all
can't
the-
think of any that I
all the
missed.
guys in report.
Didn't you also just go over everything you said on
Please look over all of the questions.
Yeah, there would also be, kinetic energy. Angular kinetic energy. What do you think it is? See if you can guess. Since all these are analog.
M times
W.
delta.
Well, what's the analog for m in rotational motion?
I forgot already.
I.
Delta, alpha, I.
So 1/2
I.
I
W squared.
omega squared. Very good.
Oh,
I see, but T squared.
Wait, so
Okay, what's it normally?
There's a good summary of the equations. There was one more that I forgot. There's you guys remember P was momentum, and that's mass times velocity, right? What we did for the conservation of velocity. Okay, well, the analog for P in linear momentum is L, and L equals, what do you think? I times what? I omega, perfect.
Wait,
And angular momentum is conserved as well, just like linear momentum is.
So L is momentum in rotational movement.
Uh-huh.
Can you define omega?
omega is the change in angle or the angle, the,
Change in theta.
yeah, change in theta over change in time.
So velocity.
There's a lot of equations for this little.
They're just.
It's all the same equations,
Just
just,
substituting.
yeah. It's all equations you've already learned, you just substitute the
No,
variables.
I know about like all the, like, what omega equals, what theta equals, what fish equals,
Alpha.
alpha.
I have a question about the portfolios, Mr. Manis.
Yeah.
Are we done?
Yeah, I think I'm gonna cut it off here.
Okay.
Here, let me stop recording.
What is this gonna be under for you?